Picture a ball resting on the floor. A push starts it moving. Now, picture the same ball already rolling. A sideways hit can redirect it, while a forward hit can increase its speed. What connects these changes? In each case, a resultant force changes what the ball would otherwise do. Without one, an object remains at rest or continues at constant speed in a straight line. Several forces can act on one object at once, so we replace their combined effect with a single force, called the resultant force. This does not mean the other forces disappear. The resultant is a model of their overall effect. If the forces balance, the resultant is zero, and there is no change from rest or constant straight-line motion. A non-zero resultant can produce acceleration. Along one straight line, choose right as positive. Suppose two people push a crate with forces of 18 newtons and 7 newtons, both to the right. The resultant is 18 plus 7, which equals 25 newtons to the right. If the 7 Newton force acts left instead, calculate before listening. The vector sum is 18 minus 7, giving 11 newtons to the right. Velocity includes both speed and direction. That is why a resultant force can change velocity in more than one way. It can make an object speed up, make it slow down, or turn it. Look again at the rolling ball. A forward resultant changes its speed. A sideways resultant changes its direction. In either case, the velocity changes, so the ball accelerates. Supplement material gives the quantitative link. F equals m times a. Here, F is the resultant force in newtons, m is mass in kilograms, and a is acceleration in meters per second squared. Force and acceleration point in the same direction. A 3.0 kilogram trolley has a resultant force of 12 newtons. Substituting, 12 equals 3.0 times a. So a equals 12 divided by 3.0, 4.0 meters per second squared. A tempting idea is that an object needs a constant forward force simply to keep moving. Test that claim against the rule. If the resultant force is zero, must the object stop? No. It may remain at rest, but if it is already moving, it continues at constant speed in a straight line. A resultant force is required to change that velocity, not to maintain it. Circular motion is supplement material. Imagine viewing the velocity arrow of an object at several positions around a circle. The arrow remains tangent to the path, so its direction continually changes. A force acting perpendicular to the motion turns that velocity toward the inside of the circle. The object can therefore accelerate even when its speed stays unchanged because its direction is changing. Keep mass and radius constant. Increasing the perpendicular force increases the speed. Keep mass and speed constant. Increasing the force makes the circular radius smaller. Finally, keep speed and radius constant while increasing the mass. What must happen to the force? It must increase. These are qualitative supplement relationships. You should compare one change while holding the stated quantities constant. Solid friction is a force between two surfaces. It may impede motion and can produce heating. Drag is friction acting on an object moving through a fluid. through a liquid, such as water, or through a gas, such as air. These forces matter when finding a resultant because they may act against motion. Do not treat friction as automatically equal to a driving force. Compare the forces given in the situation. Forces can also change an object's size or shape. To investigate a spring, measure its original length, apply a known load, and measure its new length. Extension is the new length minus the original length. Repeat for a range of loads and record paired values of load and extension. A ruler fixed beside the spring and readings taken consistently help you plot a load extension graph for the elastic solid. On a graph with extension on the horizontal axis and load on the vertical axis, inspect how the plotted points change. At first, a straight line region shows that load and extension are proportional. Supplement material names the end of this relationship the limit of proportionality. Identify the point where the graph first stops following that straight line pattern. Beyond it, equal increases in load no longer produce equal increases in extension. In the proportional region, supplement material defines the spring constant, K, as force per unit extension. K equals F divided by X. F is force in newtons, and X is extension in meters, so K is measured in newtons per meter. On a graph of load against extension, K is the gradient before the limit of proportionality. A steeper straight line therefore represents a larger spring constant. Predict what happens to the graph-based spring constant once loading passes the limit of proportionality. Can one unchanged gradient still describe the whole graph? No. Beyond the limit, load is no longer proportional to extension, so the graph is not one straight line with one constant gradient. This point is about proportionality. You're not required here to use the separate idea of an elastic limit. Transfer the model to a car. From rest, the driving force exceeds the opposing friction and drag, so there is a forward resultant, and the car accelerates. At steady speed in a straight line, what must be true of the resultant? It is zero. The forces balance, although individual forces still act. For a fresh case, imagine the driver increases the driving force. Compare it with resistance, find the resultant, then use F equals m times A. Your compact self-check is velocity changes only when the resultant force is non-zero.